know, it's just 1 or 2 milliamps. Except that these cells, the rechargeable cells, only have a capacity of about 40 milliamp hour. And that means that if you go to bed and leave this charging, in a couple of hours it'll have charged it, and then it will keep charging it, and the voltage will rise, and it will rise, and it could theoretically go up to about 5 volts, which is not very good for a lithium cell. It could actually cause it to fail. I'm not sure I've ever tried that. And the circuitry is spectacularly optimized. So here's the circuit board. It's only got the transformer on this side, an electrolytic capacitor for the low voltage side, and the 2 LEDs on the spacers on this side. It's got the switchboard power supply, which is based on a single transistor here. Oh, hold on, you know, I can show you much better than this. I took a picture for the reverse engineering, that's why it's all scribbled on. So let's zoom up a bit. So here's the switchboard power supply. In fact, let's just zoom in the switchboard power supply a bit. And it's interesting to know that the rectifier is just a single diode, and there's no smoothing capacitor, so literally this switchboard supply only rides 1/2 of the sine wave and switches during that time along that portion of the sine wave. And it's got feedback. I've drawn the schematic out, and in fact, you know what, I'll show you the schematic first, after I've shown you what else is in here. But suffice to say that that's the mains power supply. Comes in, there's a single rectification diode at this side and the electrolytic capacitor down here. Then there's a transistor to switch the charging current, and then this chip here, which I thought, oh, that's going to be something like a TP4056 or something like that, you know, a standard lithium charge controller set for low current. It's not. It's a dual op amp. It's an LM358, and it's also got one other IC here, which I've TV431, is it? I think it's no, it's not TV431. I'll just call it 431. That's good enough. But it's the programmable shunt regulator. In this case, they've common to the pins together, so it programs it at its default shunt voltage, which is 2.5 volts, and that's being used as a reference for this chip. So let's take a look at the schematic. And I've drawn it as 3 sections, because it technically is in 3 sections. So the first bit to look at here is the power supply. The main supply comes in here. The live goes through this 10 ohm resistor, well, live or neutral because it's not polarized. Goes through a 10 ohm resistor which acts as an inrush current limiter and a fuse. It goes through that big diode. Let's bring the picture and I can show you the components here. So it goes through this 10 ohm resistor, this diode, and it goes to the one end of the primary winding. The primary winding is switched by this transistor, and it's a very ordinary transistor. And on the emitter of the transistor, it has a 30 ohm resistor, and that made me think this must be used for some sort of current regulating thing, you know, to stop the current going too high. Because if you're putting, say, 0.6 volts into this, or whatever volts this thing's putting out, the feedback winding, then as soon as the current reaches a level that the voltage across this resistor rises up to about 0.6 volts or whatever it is, then the transistor will start turning off, and it made me wonder, does this operate much in its linear region? So I got the thermal imaging camera, and yes, it does operate in its linear region quite a bit, because it is very, very hot compared to the rest of that bit. In fact, it's the hottest component of the circuit board. I'm not sure. I used a magnifying lens in this, so the 101 might be an exaggeration. Not sure. I think the 84 might be closer. I'm not sure how that goes. I've not compared heat points with the magnifying lens versus just the standard lens. The feedback system is very, very neat. When the circuit's first powered up, the transistor has a pull down resistor to keep it turned off. But current starts flowing through this 330k resistor, and it starts turning that transistor on. When it does, this winding starts inducing current in this winding, which then goes through the 60 ohm resistor and this capacitor, blocking capacitor, and feeds the base. And that effectively has an amplifying effect, that the more current flows, the more this, the higher the voltage in this, and it creates a sort of feedback loop, up to the point that either the core is saturated or this capacitor is fully charged, and then no current will flow, and then it will collapse. And when it collapses, The magnetic field it's put into the coil does two things. And the secondary winding, it charges this capacitor via a diode. Note that the diode is in the negative rail instead of the positive rail. That's just what it doesn't really matter. And it puts out roughly 8 volts. This is not an accurate power supply. Floating, the voltage floats up to about 9.23 volts. When it's loaded down with the charge current, it's 7.28 volts. So it's not that sort of accurate. However, there's feedback in the form of this winding. This winding does double duty. It's not just the feedback to the terminal transistor on, but when the opposite polarity, when the field collapses, depending on how much this side loads it down, a voltage will be induced across the feedback winding, and will, via this diode, it will reverse charge this capacitor here, and that capacitor, that's this capacitor here, and it effectively goes negative with respect to the 0 volt rail of this circuit. And that means that in order for this transistor to turn on, you've not just got the just the 0 volt to actually exceed with your feedback signal, but you've got the Zener diode here that you have to exceed the voltage of that Zener deducted from the capacitor, so to speak, before that will turn on. It means that if this side is lightly loaded and the voltage floats up high, what that does is it basically turns this switching circuit off or reduces its output to match. So it's really well engineered in the sense that it's just optimized to use a single standard high voltage transistor. This transistor is rated 400 volts and they're using it in rectified 240 volts AC, which is going to peak about 350-ish volts, so it's pretty close to its rating. But it's a very simple circuit. Every component counts. It's kind of interesting in its own right. But let's, now we've got our 9 volts or so, or 8 volts. Let's take a look at the first section of the circuitry, and that's the charging section. So here's our 8 volt rail, here's our 0 volt rail. I'm not sure what the isolation is like. I may do a high voltage test on it later, but it's a tiny transformer. They've got a massive, by Chinese standards, they've got a massive gap on the circuit board between the main side and the low voltage side, which is impressive. It all depends on how well separated the windings are on this transformer. It certainly doesn't meet what you'd call UK standards in terms of well, I don't think it's using the double insulated or triple insulated output. I think it's just using standard copper wire. Yes, it is. And there's a very good chance that it's wound in fairly close intimacy to the higher voltage windings, so I'm not sure what the separation will be. Oh, one other thing that I didn't mention about the switching circuit. It has a 68k resistor across the primary. I think that's just a very simple way of just shunting the spikes. I was going to say peaks, I was going to say spikes, I said speaks. That's what happens. So when that transistor turns on, you can often get quite a spike across that. And normally the circuit that's used to suppress that is a capacitor and diode and resistor arrangement. But in this case, I wonder if by putting a resistor across that to damp it, it just provides an alternate path for that current and just limits the level of that peak, which can be modestly high given how close it is rated to the transistor's rating at the peak mains voltage. The charge circuitry consists of this. There is a voltage reference over here. And, well, what's the best way to start here? Yeah, okay, here's the op amp and a voltage reference. The voltage reference is the, what is the number actually printed on that? Am I going to be able to read this? It just says 431, which is reasonable enough. It's a mass cloned component. But the idea of the 431 is that you've got, it acts as a programmable shunt. These are really commonly used in a lot of switch mode power supplies for feedback. And you can set the voltage at which that starts conducting. And it means that if you put the LED in the feedback, the opto-isolator, then as soon as you reach the pre-programmed voltage, current will start flowing through that LED and it will give the feedback. That's in other supplies, it's not doing that in this one. In this one, it's got from the positive rail, it's got the transistor or a 2K resistor, and this 2K resistor here is like the naughty one. It's like, what on earth are they doing? But the 2K resistor lets some current through, then there's a 2.2K resistor, and then this caps it at 2.5 volts. 2.5 volts is its reference voltage. When you're dividing it down, you have to use a resistive divider if you're going to use that for a different voltage. But in this case, if you just short the connections together, it is 2.5. So the input to this op-amp is 2.5. The voltage across the cells is measured by a potential divider compared to that. Here they've got two resistors in parallel, 3.9K and 10K, and they're forming one resistor. And the reason they've got two is so they can fine-tune the value. The other part of the divider is just a standard 5.6K, and ideally you choose those values so that you reach, when this is reaching about 4.2-ish volts, then this will go up to about 2.5 and it will match the 2.5 reference, and that's what an op-amp does. It looks for, it compares the input voltages, and when they match, or one goes higher or lower than the other, the output will change state depending on where you've got them connected to the negative or the positive input. The output then drives the transistor. So normally if the voltage is low, the output will be high, and it will, or should I say it will be low, because that's a PNP transistor. There's the resistor to keep the transistor off. Here's the resistor that turns it on by putting it low. And there is the main current limiting resistor to the cells, the 150 ohm resistor. The cells are just in parallel. I'm not sure I'm keen that, because it means if you've got a really flat cell and you've got a fully charged cell, one could be at a voltage of 3 volts or less, the other could be a voltage of 4.2, and you're basically just connect them in parallel. And these things are not designed to take a high charge current, so I'm not sure that goes. I think a modest amount of current could flow between them. It would have been nicer if they just used a separate resistor for each of these, but they didn't. Other things, the output from this op-amp also goes to the LED circuit, but fundamentally what you see here is the charge circuit, and the problem here is that resistor is just, even when this transistor turns off and it should stop the charge current, then that resistor is going to leak current. That's where that current is coming from. It's forming a sort of potential divider with this and the voltage reference here, but there's still enough to push a bit of current through this 150 ohm resistor. I don't know why they've got this resistor. I really don't know why that's there. Why didn't they just take the 2.2K straight up to the positive rail to provide that current for the voltage reference? I'm very tempted to try that and see if it fixes the problem. It's very strange. But anyway, the output of the op-amp goes to LEDs, and this is where I thought one of the LEDs was a flashing LED, but it's not. Only one half of the op-amp has been used, and the other half is used to flash the LED. So here's that signal, and when it's high, when it's finished charging and it goes high to turn that transistor off, then the green LED here lights. But when it's charging and it goes low, this LED can light, but only when it's enabled from the op-amp here. So what they're doing here is they've formed an oscillator with feedback and also a hysteresis point. It's all very clever. It's quite an educational circuit. So initially, say for instance that the output of this is high and the LED is lit. If the output is high, then this potential divider is it's a moot point. It's not really in circuit. So the positive connection, the positive input, should say, to the op-amp is floating near the sort of rail. And this capacitor charges up until the voltage across it reaches the rail, the same level. And as soon as it does, and the output starts changing state, it will start going negative. But when it does so, because it's then pulling this potential divider down to the 0 volt rail, suddenly the voltage level on this suddenly drops to the sort of close to the 0 volt rail, and then the capacitor then starts getting discharged via this resistor again, and it forms, basically it goes in a loop until it reaches each of those thresholds. It's almost like a Schmidt trigger. It's a very interesting way they've done it. It's a fairly standard op-amp circuit. This is how a lot of circuitry used to be designed before MD started using microcontrollers. And that's it, the output, as well as doing the charging and the changing the voltage threshold. Also goes through this 1.5k resistor stream, which seems quite ungenerous. It's quite a high value. And it makes the red LED light dimly and flash on and off. And the point at which the green's lit and the red on it is the point that the charge detection circuit is in a sort of midpoint between the two power rails. It doesn't just suddenly snap between the power rails, it gradually makes a transition, and that's why both of them lie together. But now I'm very intrigued. I want to make a modification to this and see if it helps. So what I'm going to do, I'm going to remove this 2k resistor completely, and I'm going to take this connection here and take it direct up to the positive rail. So that means this will get its current for its voltage reference, the 2.5 volt reference, and there will be no current leaking through here. I'm not sure why they didn't do that before, but on goes the soldering iron. I'm about to do that, so this may take a bit of fiddling about. Should I do it while the camera is running? The soldering iron is going to have to heat up. I shall pause momentarily. The soldering iron is hot. Let us attempt this surgery. I'm really crap at surface mount, so I want rid of this resistor here. So I'm going to try and heat the solder on both sides of that, just basically ping it off the circuit board. That went better than expected. The resistor appears to have either bridged something else to the circuit board, or it's come off completely. I think it's come off completely. That's good. The other resistor I want off is this one here, which is the current reference resistor. So let's heat that one up by just using brute force and ignorance, and wipe the resistor off. Likely the resistor's just sticking the solder iron. Okay, this is good. This is good. It's all going to plan so far. Plenty of time for it to go horribly wrong though. Let's crop this lead of this argon resistor down to a suitable length and tin it. So let's tin the end of this lead, flow some fresh and juicy lead-based solder onto the shunt regulator here. Try not to reflect the... Oh, let's get some solder onto the regulator, not just try and ram the resistor straight on. Let's get some fresh solder onto that. Oh, that's quite good. It's very juicy. Always use lead-based solder for home stuff. It's just so much better. Leave the lead-free stuff for the fishy stuff. So that is one end of the resistor soldered onto there. Now I need to find a place to put the other end of the resistor, which is a positive rail, and that just happens, the closest one happens to be the transformer pin actually, which is the positive rail. That's fine, the transformer pin it is then. So I shall flow some fresh solder onto that. Put the resistor down a wee bit onto that, and then flow some fresh solder on again. To make a connection, just leave that resistor floating precariously above the circuit board. So let's see, am I in shot here? Yes, I am. Let's flood that on. That looks pretty good. And just crop that lead so it doesn't go anywhere it shouldn't do. Using different snips. Cheap eBay snips, but different ones because the other ones I tried to cut some that was way too hard with them and ruined them, as you do. So let's shape that up a little bit. Let's bring the meters back in and see if that's fixed it. It may be the circuit has been so optimized that it's got that doing that might not fix it. I think that'll fix it. Unless there's some other current route through that that leakage current can still find its way, but I don't think there is. So let's connect this meter to here, connect that to here. It's worth mentioning when I got this that the contacts, one side worked fine. I kind of expected these to be on the circuit board, but they're separate. They're actually pressed into the plastic housing. One of them was fine, but the negative connection on one side was not making a connection. When they pressed it in, it just bowed slightly the wrong way. So let's get the quick test. One quick test. Plug it in and see if it disappears in a puff of copper with an ear-shattering explosion. Okay, let's turn that on. Good start, the green LED is lit. Let's find a cell, plug it in. It's still showing 2.5, but that source of leakage current should be gone now. So if I let that charge fully, it should theoretically turn, it should go below that. It should reach the point that there is no residual charging. What voltage is across that zone? I may have to pause while it charges up to the full thing and then tell you what the result was afterwards. Let's measure across this. Keep my fingers away from that circuit board there. The voltage is currently at 4.15, so it's not quite reached the end of charge yet. Okay, I shall give that some time, and then I'll have to come back after that, so there will be a slight pause. Now, while I was making this video, this lamp rolled onto the table just as I was preparing, and I was hearing the rattling about, I opened it up, and it's because I'd taken the circuit board out and put the contacts, the press-in contacts in the back, I'd put them inside it. And I was just thinking, I shook this, it was like a wee maracas, so and it made me think, see, I was at primary school, and primary school in the UK is, you go there from about the age of 5 until about the age of 11 before you go to secondary school. And the teacher told us one day to bring in a glass light bulb and the core out of a toilet roll, the little cardboard tube. And we brought these in, and she had newspaper, and we taped the light bulb into the toilet roll tube, and then put paper mache all around it and covered the end up, and we were like, what's this about? And after we'd done it, and like after several days, the paper mache set completely, the teacher came out and told us to smash the thing on the windowsill, and you heard all the glass break inside. Keep in mind, this is primary school. What we just meant was a maraca full of broken glass. That's just ridiculous. It's so funny when you think about it, that you think of all these sort of PC things these days, that here we are with these little, we're all running around shaking our glass-filled paper mache maracas. I thought that was great. Well, at the time I really thought it was great. I didn't kind of think about things. But, right, I'm going to leave this charging for a while, and I'll be back shortly. So a short time later, the current is now gradually reducing. It's down at about 50 microamps now. So that has solved that residual leakage problem. And the voltage is stabilizing out at is 4.16 is where it's more or less ending the charging. So that's kind of fixed that. It's not ideal that you'd have to do that. The final test I want to do with this then is electrical separation using a high voltage test on it. So let's bring the gear up for that. And I should get the something on for that so I can tack some leads onto this. So this incidentally hasn't fixed the reverse discharge thing. That's a bit trickier. You could theoretically put a diode in, but then you'd have to allow the diode drop, then with the charge voltage variation, you'd have to allow that on it to typically end about, instead of 4.2, it'd have to be 4.2 plus the diode drop. It gets a wee bit tricky. This is where dedicated chips really sit in the TP4056 that basically just disconnect the battery completely when it's fully charged. Right, so let's get this out of the way. These meters, the wee GP meters, are ideal for applications like this. It's just a wee extra bench meter that you can just stick in and leave in at one setting. I like the fact It's a weakness as well. I like the fact it's got the current range on the same connectors here, but that's also a weakness since it means if you're messing around the meter, you turn it up to the, if you turn it round in the direction of current range when it's connected to a voltage supply, it will just blow the fuse in the meter if there is one. So let's, the solder iron is just about up to temperature, I think. Let's bridge these two connections together. Because one of them is connected to the, do I want to do that? One of them is connected to, one of them is connected to the coil, one of them is connected via the diode. Or do I actually want to bridge wires right across? What I really want to test here is between the transformer and this side. I'll just solder a couple of leads on, that's the best bet. I shall bring up yellow wire, yellow for hazards, and strip it. I'm wanting to test the electrical isolation of the transformer, so what I'm doing here is I'm commoning the two primary coils, the primary and feedback, and I'm also going to connect onto the output with the other winding, other wire, and that will give an indication of the resilience of the insulation. Where's the solder? What am I doing with the solder? I put the solder over here. So let's tin this wire. Let's find my transformer connections that I want to go onto. I wouldn't be using this to charge lithium cells because it's just not ideal for it. It may not be suitable for charging lithium cells by the time I finish this test. If it does it. The camera has just started again, I think. It's got that file size limitation and it'll start recording. Yeah, it has. I just heard it go ping and stop momentarily. And then it starts recording the next section of the video. That means the video has gone on for quite some time. Sorry about that, but it's quite a complex video. More complex than it was originally supposed to be. It was like, hey, can you use the batteries in these? No. It turned into something much more complex, but much more interesting. And the length of the video doesn't actually take into account the amount of time it took to actually reverse engineer this. It was fun. It's like an electronic puzzle. So I'm only going to connect to one end of the windings here because the impedance of or resistance of the coils is so low that it doesn't really matter. You don't need to connect to both ends. Righty-ho. Let's get I'll leave the solder iron on the fire. Let's bring the electrical tester up and brutally assault this with electricity. So I need to strip these, strip that, make sure all the other wires are kind of out the way, and bring the tester up. Here's the tester. Getting the lead for the tester would have been quite handy. Let's sort these leads out. Oops. So I'm going to connect the ground lead to one of them. Let's zoom down onto this unit here. Let's zoom down onto this. This is the bit we're interested in. And I'm going to trap the other lead by twisting it together and then stuffing it up the end of this probe in a non-compliant manner. Is this going to jam properly? Yes, it has jammed properly. That may kind of release the level, see how it goes. So here's the little circuit we're going to be testing. I'm just going to get a lead for this tester. Yeah, I knew that was going to ping out. It's not how you're supposed to use that, so let's get this in here. I may have to get scientific about this, or maybe not. I'll just get more brute force. I can almost hold the trigger in my hand. Right, let's test this. Let's make sure all the leads are nowhere where they can actually do some damage, because everything will be at very high voltage and listen to this for a while. Yeah, that looks pretty good. Let's get everything out the way. Let's turn this on and crank it up to 2000 volts and see if that flashes over. This time there's no class Y suppression capacitor to worry about. Let's take the exposure off to brighten this up. There we go. 600 volts, 800 volts, 900 volts, 1000 volts, 1300, 400. Very little leakage at this point in time. 8,000, 1.9,000, 2,000. Getting a very slight leakage, but that's capacitance between the windings probably. There's no class Y capacitor in this because there's no lead in it. I guess they reckon it's not really needed for that. Should we go up to, I can't go up higher, I can go, I can put it to the 4,000 volt range. Will we go up to 3,000 volts AC? Yes, we shall. Let's rock it right up to, some would say 3,000 volts AC is a good test for this. I reckon 2,000 volts AC will be peaking at sort of 3,000 volts region. I can hear corona. I can hear buzzing. I can hear corona discharge, but it's made it to 3,000 volts. It's making fuzzing, buzzing noises, but that is probably corona discharge. It's holding up. That's quite impressive. That is very impressive. Should we just destroy it? Should we go up to 4,000 volts? Yes, we shall. So I'm setting the leakage to just 1 milliamp. Oh. Now, did it arc across? Hold on, that's not set to 1 milliamp then. Let's see what actually happened there. Can you hear fuzzing and buzzing? The current's quite low, it's only about 50 microamps leakage. I'm guessing that if it tripped, that is arcing across, but it's doing so at 3,450 volts, which is reasonable enough. And just out of interest, what happens if I bump it straight back up to 2,000 again and just leave it sitting there for a while? I want to set it way up too high. Still getting used to this thing. I've been over greedy again. If you set it to 2,000 volts, as soon as you exceed the 2,000 volt test, it won't let you go any higher, and it cuts it off to 0. So it's still holding up. So it was kind of arcing over somewhere. I wonder if that was arcing between windings, but 4,000 volts is quite a bit to hold up to. Well, that was 3,500 volts. So I suppose that technically speaking, it's kind of passed, hasn't it? So yeah, it's an interesting, but to be honest, I wouldn't really recommend them because it has that built-in weakness. It seems like it'd be quite a useful little thing to just have that facility to just ram a couple of button cells into it and charge them. But as I say, if you leave it overnight, it could potentially charge these up to quite high voltage in its original circuit format. So possibly, really just a feel then, I'm afraid.